i's here run from 1 through n, add them all up. Okay, so this is maybe a new symbol for some people. It's a summation. It means add things up where you run through each instance 1 through n. Or excuse me, k in this case, because I was thinking of this in RK. Okay? Right. Inner product. Okay. What does this do for us? Well, it's a notion that actually has some important geometric intuition, which you've studied some already in multivariable calculus or linear algebra. One of the first things that you can do with an inner product is define a norm, which is a notion of length. In linear algebra, you might, for instance, call this the length or the magnitude or the absolute value, symbol sometimes used. And you define this to be the inner product of x with itself, take its square root. Okay. Really? Why? Why in the world would I think about doing that? First of all, can I even take the square root here? Well, what happens when you multiply, take the dot product of x with itself? Each of these entries is a square and therefore not negative, right? It might be 0, okay? In fact, the only time it is 0 is if everything's 0. So the only 0 has the vector 0 is norm 0. But the point is the square roots are possible, and then you have a length. And this length corresponds with the geometric notion of the Euclidean length. You know, so if you have a point here, x1, x2, then this length is going to be the norm of x, the length of the hypotenuse. There are lots of other notions of length. And of course, when we start talking about the word metric space, we will be, in fact, working intimately with notions of length like, but not necessarily the same as this one. Okay, very good. I think that's all I want to say right now about the Euclidean spaces, but we may return to them soon. Now, it turns out that there's another way to, if you like, extend the reals in such a way that you, in fact, do get a field. Okay? This creature's not a field. We don't have a natural notion of product that has the right kind of notion of inverses. But you can define an extension of R. In fact, the set itself will look like R2, but it will have a field structure. So let me just mention that these are called the complex. This is the complex number field. And the point is here that R2 can be given a field structure. It's just not the one you might first think of. And what do you mean by that? Well, what I mean is you give me ordered pairs, and I know how to add them. That will be just like I expect. In fact, I'll put a comma here. But the multiplication, well, that's a little different than you might expect. We're going to, rather than straight multiply elements, we're going to twist our construction in a most interesting way. In particular, I'll let the first element be AC minus BD. And then the second element will be AD plus BC. Interesting. That's a very funny notion of multiplication. But it does indeed yield a new two-dimensional ordered pair, right? Okay. And so now the question is, why is this a field structure? I have a multiplication and an addition, and of course the point is this is a field because it'll satisfy all the axioms. You just have to tell me what the 0 and the 1 are. What is the additive and multiplicative identity? Here, what plays the role of 0? The 0 of the field, this is when you say 0 of the field, you mean the additive identity. And the 1, okay, now what do I mean by that? I just mean the additive identity, right? We're not searching for the 1, right? This is the additive identity, right? What is the 1? The multiplicative identity, right? Yeah, not additive, multiplicative identity. Well, you can check that the multiplicative identity is actually pretty simple too. It's just 1, 0. And I'll let you check these things. But convince yourself of this. If I put if I let C be 1 and D be 0, then these two terms drop out, and you get A comma B, right? There's a little more work to verify that there are inverses, but this is all rather nice. Okay. Now, the other thing that's great about this is that this complex number field actually does extend the reals in a natural way. So first of all, let's call this field C, which is, so it's basically this. It's a set. As a set, it's equivalent to R2 with plus and times as above. Okay, but the point is, with this additional structure, we'll think of this as the complex numbers. And here's a point we want to make. C extends R in a very natural way, in much the same way that R extends Q, right? And Q extends Z. There is a subfield of C that behaves just like R. Really? What is it? Yeah, let's look at all ordered pairs A comma 0 where A is in R. This, if you just make all the B's and D's here 0, then in fact you just get the usual addition of the first coordinate, and in the second coordinate, here this is 0, and this thing just becomes the multiplication, right? So in fact, this set behaves, is a subfield. It behaves like R. So it's a subfield. Another way to say this is it's a subfield isomorphic to R. If you know that word from algebra, fine. If not, all it means is it behaves just like R, your usual arithmetic on R. Oh, that's great. It's beautiful. So because of this, and because of the following property, so here's another thing to notice. If I look at the element 0, 1, it actually, you can check that 0, 1 times 0, 1 under this arithmetic is just, well, let's see, all the A's and C's are 0. And that makes this 0, and that makes this minus 1 times 1, which is minus 1, 0.